So thank you, thanks for letting me come here. First, I apologize. I got a lot of material for 20 minutes. I'm gonna probably go pretty fast. I'm gonna try to be accessible to being very nerdy and also being accessible so that if you don't know this, hopefully you'll still get something out of it. A quick about me, I work at Armstrong World Industries. I'm the tech lead for their website. I've been doing this I've actually been on the web team there for the last 25 years at the same company in IT doing web stuff. It's kind of freaky. So that's the quick about me. So if you get anything, basically here's the whole talk. What's new in HTTP3? The Quick Transport Protocol. So it's QUIC. I believe it's pronounced quick. If I didn't, well, I'm just going to say it that way for the rest of the talk. The next up is TLS all the things. TLS meaning SSL. Everything's secure by default. Next thing is QPAC. It's a replacement for HPAC. If you don't know what HPAC is, I'll explain it a little later. And improved server push. Yeah, it is what it is. So what is quick? This is going to be a super quick overview of quick. I'm going to, no pun intended. Then we'll talk about it a little more later. But it's pronounced quick. It's an attempt to do the TCP protocol, but you're doing it over UDP. So if you remember hearing TCP IP, so IP, everything goes on that. TCP is one protocol, UDP is another protocol, and that's all the more in depth I'm going to go at the moment. What we're going to do next is jump back in time. So why are we going to jump back in time? Well, to learn why HTTP3 is going to be good, we need to find out what 1 and 2 were doing. So what is HTTP? Whew. It's a lot of different protocols at the same time. This slide here doesn't even encompass all of the RFCs that make it all up. So you have, and actually the craziest thing, so I wrote this talk actually about 3 or so years ago, just never gave it. And then when I came back to it on the Tomcat users list, I belong to those folks over there. We saw an update, and it's like, wow, this June of 2022, they just released new editions of everything. So of semantics, of caching, of HTTP 1.1, of 2, and then 3 actually in official form. There's also a couple other companion RFCs like HTTP state management. That actually dates back to 2011. HTTP state management, a fancy word for cookies. So cookies are just a crazy thing. So I've been doing this for 25 years. I remember when cookies first came out. And I still do things on the 2001 version of cookies. And I keep on forgetting that 2011 fixed so many of those problems. There's also another one here, I call it out, 3896, all about URIs. The reason I posted an obsolete one is because it was replaced by 3 other ones, and that doesn't even encompass everything that involves HTTP. So if you get really bored one day, start reading these. They're really awesome to read, but they can put you to sleep. So let's dive back to HTTP 1.1. It's got a lot of additions to it. Just going to show you, like, it has been revised over time. So even though it's 1.1, it actually has a couple different additions to it, a couple different versions. Why are there a couple different versions? Because over time, back in 1997, when we decided we're going to come up with 1.1, it started working one way. And so does everyone know what an RFC is, a request for comment? So a request for comment, I'm just going to beat this to death. A request for comment is a company or a person or a little bit of combination of both, a group, a consortium says, we have this technology, here's how it works, and here's how we think it works. And so if everyone wants to use this technology, this interoperability, here's the description. And of course, every description is going to be wrong over time, so it gets rewrites. And not rewrites, but more like clarifications. That's what all these future editions do. So as we talk about 1.0, 1.1, 2.0, and 3.0, here's a quick overview of all their differences. And we're going to go a little more in depth into all of these. So 1.0, back in 1996, and there's actually a 0.09, but that never made an RFC. 1.0 was nice because it was finally a standard, but it was horrible because it didn't do a lot of things. But at least everyone was talking on the same page and not doing crazy stuff back in 1996. 1997, the best thing they did was they split the semantics and syntax. What is semantics and syntax? Semantics is, okay, so we're going to say stuff, and here's how we're going to define what it means. And then the syntax is, how are we going to say it? Is it this colon equals stuff? And what happens with the carriage returns, the line feeds, the character encodings, and all that kind of stuff, all that definition in the syntax. Then when you get to HTTP 1.1, it also gave us host headers, virtual hosting. HTTP 1.1 still absolutely beautiful to use today. In fact, it gives us the keep alive header, so some of the performance issues, not too bad. But for people like Google, Facebooks, and all that kinds of stuff, they need more performance because there's defects. So that's where HTTP2 came into play. HTTP2 gave us things like, let me take a step back. HTTP2, in a quick summary, is more network oriented. So let's optimize going back and forth. So the semantics, the syntax, so how the client and the server talk to the web browser, the web server talk to one another, essentially the same in 1.1 and 1.2. How they say it at a network binary protocol kind of changed. Not drastic, but big enough to make a version change. Then when you get to HTTP2 to HTTP3, everything's out. So everything before was TCP related. Now we're UDP related. So totally different protocol. And we'll talk a little more about Quick as we go along, but I'm really fascinated by what you can do with Quick in the future. So Quick is actually a fairly generic protocol that HTTP happens to be the first big thing really using it. So let's rewind again back to HTTP 1.1. So a sample request is going to look like get. So you'll see get, post, put, delete. And then you'll see what do you want, and it'll always be a path, and then the version, and then you'll get a couple headers, and that's a normal request. So between HTTP 1, 2, and 3, logically this is all the same. Great. And then what's going to come from a response? It looks a lot alike, honestly. You get the first line looks like, you get a response header. And you get a protocol of like, yes, I acknowledged it. So you'll see 200 as OK. You'll get 300 class for redirects, 400 class for errors, 500 class for server-side errors. So 400 is client-side errors, 500 is server-side errors. And then you'll get a whole bunch of headers. So what all these headers mean, they're in the spec. But what you'll notice is I do have two in italics, so upgrade and connection. So this is an HTTP 1 request, 8.1.1 request. So what the server's coming back with, it says, hey, I speak HTTP 2, so if you want to make new requests to me, I'd be happy to talk that. So it's an opportunity to upgrade to the next level protocol there. So the other big thing to call out at the moment is HTTP 1, the request, response, all text. So what was really cool back in the old days was I can telnet to a server, start typing all the livelong day away, get my request, and then I can see my response. So if I would have said head, so I only want the headers coming back, I can just telnet in. Telnet's available since like 1970 something. And I can just, easy debugging. The only debug tool I ever need anywhere is Telnet, and Telnet was always available anywhere. Yahoo. The downside is it's all text. Yep. So the upgrade H2, H2C, that's the messaging and I don't know the actual specifics to those, but that's really the queue for the web browser. As the web browser receives that back, that says, hey, you can upgrade to the next, you can upgrade to HTTP2 because I offer that as an option.
Yeah, H2C is clear text, so HTTP2 defaults to TLS, but requests some implementations allow for text.
I think that's what it.
Yeah, so I think it would be, this is all client dependent, but it would evaluate in order of, so preferring first an HTTP action over TLS and then following back to HTTP.
Yep.
So it's my clarity when you were talking, I was thinking there might have been a negotiation going on
if I understand what you're saying, the initial request saying this is what I can speak.
There is a way, I believe there is a way to upgrade right away. You won't get the response, you just get a different header back. So you get a different response code back. I'm going to conjecture it's probably in the 100 level, but don't quote me on that.
So that upgrade field, that does not do that, or does do that?
Upgrade is so upgrade says the server's making a request back to the client saying, so right now it's saying content length. Because it's giving you a content length and a content type, it's actually just serving the request back. But if you want to make another request after this is done with this open socket connection, you can upgrade the request to HTTP2. So the 1.1 defects, so mostly around performance. So as you saw, so browser makes a request to the server, it's one connection. So you're throttled with that one connection per request. Now, keep alive is a nice thing because you don't have to renegotiate the socket connections. You can reuse that, but you're still chained one at a time going through that. Back a long time ago, browsers had their own limits of either 4 connections, 6, 8 connections. I don't know what the limit is today. But a browser can then make upwards of 6 connections to a single web server, or actually domain. So you could actually theoretically get 6 different things coming down at the same time for various web pages on a first time load where you have like dozens of images, CSS, text, sprites, and all that stuff. 6 is still a pretty low number. So back in the day, a long time ago, people would fix this problem by, I would have www.example.com and then images.example.com or image1, image2, image3, like different domains to fake the browser out to hopefully bypass those 6 count restrictions. Keep Alive helped. Because everything was text, you have things like cookies. Cookies can be rather huge. And then the other big defect, not big, the other defect was server generated updates. So as you're getting chatbots, you're getting various things like that. Sometimes the more advanced use cases is you would want the web server to say, hey, I have a change, let me push it to you. There's no way to do that in HTTP 1. So what does 2 do? First thing 2 does is it's a binary protocol. So when I say binary protocol, because it's binary, you can compress things down. You're not dealing with text characters. You can multiplex your connections. So a single TCP connection can now send back multiple responses at the same time. So the good thing is you get multiple responses. You can get multiple responses at the same time over the same connection. That's good. The bad side was the people who were doing all that domain sharding, now that's an actual anti-pattern because you might actually open more connections. So live and learn. It'd have to be to the same host name. And then the next thing you have is HPAC. So HPAC, what is HPAC? There's a beautiful article there, but what HPAC is so as you saw those headers, some of those headers now, through the HPAC, I forget how it's defined. I don't want to say definition or standard, but through that, some of those headers can be compressed into one character, a magic number. So things that are very common like date, cookie, set cookie, accept, all of those, instead of sending all of those individual characters, you can just send a number. And that number is well defined. So right there you get a couple bytes saved. And then the content that comes along further right after it, like a cookie. So like I've seen requests now, at least on our website and other websites, you're sending like upwards of like maybe a dozen cookies back, where your total cookie size could be like anywhere from 200 to 1,000 some bytes, and then some. So now that can get compressed. So you get a huge savings. And when you're looking at a website where you're having like 60 or 70, images on a page, that adds up over time. The last part is it gives you something called ALPN, Application Layer Protocol Negotiation. It's a fancy way of saying when you're doing the negotiation back and forth, in other words, the client and the server say hello and start talking to one another and agreeing, they're doing it in less packets. So once again, the Googles, the Microsofts, the Facebooks of the world, where that first byte speed is super important, those less packets is what is really nice for them. So now we're going to go take a backwards dive back into TCP. So why? Because it would be important for the networking. So on the TCP side, let's first quick talk about when you get a connection. So ignoring HTTP, let's just say any TCP connection in general, whether it's mail, whether it's almost anything, you're going to have your client and your server. So your client is going to say, send a SYN packet to the server. So it's going to start the connection. The server is going to come back to the client to say, yes, I would happily connect with you. And then the client's going to come back and say, yes, I got your acknowledgement. So ping, pong, ping. So before you've even done anything, so just to get the initial connection, ping, pong, ping, 3 different packets, round trips back and forth there. Why is that important? Over a local area network right here, not too bad. We used to be, at Armstrong, we used to be more global at the time, so we had Australia websites, and we were, for lack of a better term, limited by the speed of light. So getting a packet the whole way around the world and coming back and going back and forth to negotiate that connection really added up. Our performance was really crappy down there. Content delivery networks help, but speed of light, you just can't fight it. So the less packets, the better. So that's one challenge to TCP connectivity. Another challenge to TCP is the awesome thing about TCP is from an application developer perspective, you don't have to worry about packets arriving out of order. So when I am typing on a keyboard or sending packets, if some of the packets come out of order, it's up to the kernel, the operating system, to rearrange those packets to get them into the right order. So if I say hello, I'm going to get HELLO if it came in each individual packet. So that's the good news. The bad news is, to do that, the server needs to send the appropriate packets, acknowledgements back saying, yeah, I got that one, yeah, I got that one, yeah, I got that one. So as you see, so even though I'm sending, even as a web server, I'm sending like 100 megabytes up and real fast, the client still needs to send a couple messages back. Even though they're acknowledgements, it still adds up. Going to Australia, long time, you got to fight the speed of light. Another problem is when you're trying to ramp up. So back in the old days where like a 10 megabit network was like, really super fast. Now that's kind of like, that's pretty slow. Ramping up to use that full 10 megabits, the server would just start sending packets faster and faster and faster. And then eventually it would get to such a speed where the client would say, whoa, too many. I'm going to lose some packets, and it'll start to send an error back, and then that's how you throttle to slow things down. So in the old days, because the numbers of how fast your network was not that big, to get to that max number, usually it wasn't too bad. Now that we are up to gigabit speeds and all that, to ramp up to there could take a lot longer. Like I said, these are more Google, Facebook, Microsoft problems. Mere mortals like us, probably not that much of a problem, but it is a problem per se. So the goal is, how fast can I send those packets out the door? So all of that being said, with HTTP2, so now you have multiplex connections. So I have client, I have server. If I can have 5 things coming down that one connection at the same time, what happens when one of those packets goes bad? It's got to get a resend. So all of a sudden, all 5 of those resources that we're downloading all of a sudden get horked at the same time. So when you have a low quality network or things like that, HTTP2 can actually perform pretty badly in some circumstances. So like over a wireless network, that's actually the case some people have found. And then I had mentioned the ramp up speed there. So Back to the original slide. What's new in HTTP3? Quick, TLS, all the things, HPAC, and improved server push. So I'm going to skip quick real quick because I'm going to hit that in the next couple slides. TLS, all the things, that's pretty straightforward. So in HTTP 1 and 2, well, 1.1 and 2, TLS was optional. So you can do things in clear text. You could do it not in clear text. I mean, you can do it securely with an SSL certificate and all that good stuff. Yay. But it was your option. With HTTP3, mandatory. And they also come up with QPAC, which is a replacement for HPAC. In my reading of it, it just seemed like the same thing. So the reason it's called QPAC, though, is because of the way the transport mechanism happens. You can actually get headers in a different order. So because the headers are coming in a different order, the rules of HPAC kind of got broke a little bit, so they just came up with QPAC. Don't quote me on that, but honestly, that's how I interpret it there. And then improved server push. So let me jump back to HTTP2. HTTP2, as you have that connection from client to server, if it's left open, there is messaging mechanisms for a server to say in a response, hey, I also have this resource over here, and I'm going to send it to you. So where that comes in handy is, where that'll really come in handy is, let's say you're trying to get someone's homepage, and on that homepage you have a couple CSS files, a couple JS files, and some images. So those things that are like, critical path, HTTP2 gives you the option to say, as you're downloading our homepage, oh, by the way, here's all the other resources that you're going to need too. So don't worry about parsing the HTML. But when you get to that HTML, here's the assets that come with it. So like I said before, it gives you a quicker turnaround time to that first page load. So with HTTP3, they just did more improvements on that. So now the fun part is quick. So the too long didn't read of quick is you have TCP over UDP with the following improvements. So it's running in user space, not kernel space. So user spaces versus kernel space. So I remember back in my college days, 20, 30 years ago, that used to be a big thing. What's really nice is in user space versus kernel space, user space, if bad things happen, you're not violating the kernel. Yay. That's all I'm going to touch on because there's so many other rabbit trails we can go on there. The faster handshake, which I'll talk about next, is with Quick, with that faster handshake, in a few packets, you can get your connection, get your TLS negotiation, and boom, you're good to go. TLS 1.3 by default, and this last piece is that connection ID. So since we're going over UDP, and I'll talk about UDP versus TCP in a moment, with that connection ID, if that connection is broken, you can still kind of, when I say connection, that TCP connection is broken, or that logical connection is broken, it'll still restart up kind of nicely. So let me start over re-saying that once more. So with TCP, remember, I say hello, I get a response back, I say hello again. And then that connection stays open, and and everything goes back and forth nicely. If you switch IP addresses, for example, you're on a mobile phone, that connection is going to get broken, gone, and you're dead in the water. As I read it with Quick, because they're doing this connection oriented, with this connection ID, you can switch IP addresses. It doesn't matter that that TCP connection is broken. And why is that TCP connection getting broken important? Well, if you had 5 things chained on that connection as you're downloading it, well, all 5 resources that you're downloading has to get re-downloaded. By using a connection ID, you can just restart where you left off.
So I'm playing in a tournament on chess.com's app. Finished one game. On my phone, I can come into the office and sit down on my computer. And I'll play the next game on my computer. That is what makes that happen.
Not quite. So because there's a sufficient lag time between the two, I'm more or less thinking with the connection ID oriented, it's more like you're driving down Route 30 and you're getting tossed from cell tower to cell tower, and for some reason that cell tower can't preserve that IP, so it pops you on something else. That's probably more the normal use case. Because you're going from office to here, the latency there you might as well just use a pigeon at that point. And there's a pigeon, there's actually an RFC out there for doing all of this with the pigeon protocol too.
I have a quick question. Running in user space, are there any security implications?
Well, when you run stuff in user space, usually you're just limited to the application you're running on then. So if something gets compromised, then it's only that application and the permission set that application's running in which can be compromised. If you have a compromise in the kernel, well, now you have the keys to the kingdom. So that's the one user space versus kernel space kind of topic people kind of jump on a lot. I wish this was a little bigger now in hindsight, but I'm going to repeat kind of what I said before. So handshake comparison. So plain old TCP, ping pong ping. So whether it's HTTP1, HTTP2, same thing. But when you add TLS to it, you have ping pong ping, then you have a TLS handshake. So with the TLS handshake, how does that work? So TLS, I mean, I'm surprised it's even that small of a number of things, because with TLS, you have to do things like, yes, I want to do TLS. Great, that's wonderful. What protocols do you use? I use this, not protocols, but what algorithms and what ciphers do you use? Oh, I like this cipher. Okay, great, you can use this cipher. Now that we're going to use this cipher, let me give you a magic number so you can solve a math problem. So then we can decide how we're going to actually encrypt it. So there's a lot of back and forth negotiations to actually encrypt the conversation. I won't go into more into that, but because TLS has so many back and forths, like I said, when you're talking to Australia to set up a TLS conversation, a lot of work to do. As opposed to Quick, at least as if this is honest, with Quick you get the handshake and then boom, you're off to the races. So that's a lot faster. So one thing I didn't talk about was what is UDP versus TCP. So TCP, it's connection oriented. It's TCP, I send a request, I send a packet of data. When you get that packet of data, eventually the other side will send a tiny packet back saying, yep, got it. With UDP, it's all connectionless. It's really more like going to the town square or something like that and saying, hi, here's my stuff, and that's about it. So with UDP, and that's kind of overstating it, but UDP is more like, I'm going to send you some packets, and if you get them, that's cool. If you don't get them, yeah, that's fine too. So the downside of that then is with UDP is you have to also create a mechanism that you can get the error correction coming back. So what I said back in the first slide was what Google and the other folks who came up with Quick essentially did was they reinvented TCP. They just did it on top of UDP. So what are the downsides? So right now UDP is not as optimized because everyone's been not using UDP for the longest time. Honestly, back in the day, a long time ago, where we used UDP mainly was for multiplexing. So it was great for like if I'm on a local area network right here and I want to stream something to everyone at the same time, UDP is perfect because if you get the packets, great, I don't care. I'm just going to send them to all, and then it's very consistent. Because UDP is not used very much, people don't know how to network manage it very well. So it could be throttled for various reasons and other traffic shaping. Who knows what will happen to it. While it's an RFC, the libraries that support Quick, there's not many. In fact, yesterday I actually went to look at curl to see what the state of curl was. And curl's support for HTTP3 is still labeled as experimental. You literally still have to build it, and when you go to build it, it looks like they give you an option of 3 different libraries to build it with. So until curl comes out with a client representation of it, us mere mortals probably won't be using HTTP3 too much yet. Is the performance worth the complexity? Maybe. Like I said, the people who came up with this is Google. So before Quick, this used to be called Spidey. And then Spidey went away and got relabeled Quick and then relabeled HTTP3. So really, who's driving this? It's really the Googles of the world, the Microsofts of the world, the folks that absolutely run at such scale that every byte counts and every packet counts for those guys. For me, yeah, I mean, I still work on the marketing website, but I have a content delivery network in front of me running HTTP2, and we try to cache things. Most of the performance stuff that I see doesn't really mean too much. For me, I work with marketing all day, and my biggest bang for the buck for performance is trying to convince them not to put 13 different beacons onto a single web page from 17 different vendors. If I can not have that happen, then I'd worry about this a lot more. That we can talk about that after the thing. It'll be an IT security nightmare. Right now, IT security, like, you know, if they want to do deep packet inspection for various things, run man in the middle, or things like that. So from an enterprise IT security or various things like that, how do you manage it? So one of the interesting sides of HTTP3 could be who knows who might set up websites that are more nefarious and go under the radar a lot longer because we don't have the mechanisms to detect that they are nefarious websites. So in a predictable network, like a data center or something like that, HTTP2, in my opinion, is probably good enough. And then lastly, one of the things is proxy servers. So we don't have HTTP2 to HTTP3 proxy servers because the protocol is totally different. So how do you use a proxy server? So in enterprise settings and lots of other settings, we're going to have a lot of challenges there.
Real quick,
Mm-hmm.
you're talking about IT security.
Mm-hmm.
Would your best guess be that Facebook's and Google's will have already solved that before they do
No, the Facebooks and Googles of the world, well, they have two different goals. So Facebook's goal is really just to keep you glued to their timeline and get engagement because you're the product. So they don't really have any interest in security, and they have a long history of that. Now, there's different lenses on how I can say that in jest. The Googles of the world, they're just really trying to make sure that advertisement gets in front of you. So their security front would be more like kind of what they're already doing today. So personally, yeah, that's.
So no network unreliability.
Say again?
Network unreliability.
Network unreliability.
That's where my question was coming.
Yeah, so where I see this really shining is really in the mobile world or the Internet of Things world. At least that's what the article said. So in the mobile world, it really makes sense right away. So if I'm driving and I have a kid in the back seat and he's streaming YouTube and I'm driving down the highway getting tossed from cell tower to cell tower to cell tower, HTTP3 is going to probably be really good for keeping that stream active for him so he doesn't get the lag and I get the whining or something like that because there's the lag. So on that side, it's going to be great. On the Internet of Things side, it kind of remains to be seen. Like as we see more Internet of Things devices pop up, you know, if they're static, is their connection going to be solid? That's what I don't know. But if there's a lot of them and weird weather conditions, who knows how that'll operate. And then last, I tried to put links to everything I referenced before. I'll put this slide out, this whole slideshow out somewhere. Not sure where yet. I'll post it in Tech Lancaster. I have it on my website. That's not an easy thing to get to, at least on here. But yeah, those links were really great to kind of give you a quick deep dive on these topics here. But really, in a nutshell, HTTP2 was network performance, HTTP3 network performance again, except it just rewrote the whole protocol. And then the last thing is Quick is pretty generic. So what's really interesting is once they perfect the HTTP3 thing with Quick, there is opportunity to use that as a generic protocol to actually do new things in the future that are not HTTP related. What are those things? I don't know, but once they have the libraries out there, it'd be kind of fascinating to see what people do with it. So that, I'm all done now. I'm sorry it went a little long, but
Just out of curiosity, how's the TLS, high-level TLS part of that actually work?
I'm sorry, I didn't.
How does TLS actually work over UDPs? Don't you have don't you kind of need that handshake between the private key transfer?
Yeah, so the question was, how does TLS work over UDP? So there is the initial, my impression was the initial handshake over gives you, they've changed the handshake that they gave you a lot more information to kind of say, what also you're dealing with TLS 1.3. So what, personally, I don't know the differences in TLS 1.3, 2, and 1, the TLSs that is. But I'm sure because they're trying to network optimize, every time they've gone through the spec, they've been trying to figure out ways of how can they shorten the life cycle. So are they restricting ciphers? Are they restricting other things that I can't really answer that one? I wish I could.
What's the actual implementation of this? So does every website need to upgrade to HTTP3? Is that like, what are the steps to getting to there?
Good question. So the question was, how do we get to HTTP3? So the good news is browsers are already, because it's Chrome and Microsoft is using Edge, using Chromium and all that, browsers are pretty good to go. So on the web server side, we're still seeing the adoption's not there yet. So you'll see adoption based on things like Google. I don't even see it in the content delivery network space yet. I've seen, I use Akamai, and HTTP2 felt like it took a while for that to even roll out. So for content delivery networks to move over to HTTP3, that's going to be a long time in passing. As for individual web servers, I belong to I'm one of the Apache Tomcat committers, so I kind of know the inside scoop there. That's not even on our radar at the moment. It's kind of on the radar, but because of the UDP issues of trying to figure out how to do this in UDP, because it's such a total rewrite, that's it's just an amazing, it's going to be a Herculean effort for a lot of the individual web server folks to kind of do that.
So unless there's a major streaming platform like the example you gave with the car, is there any reason like the average website is not trained over to HTTP3?
Yeah, I don't see, and that's it. I don't see much compelling reason at the current time to go over to HTTP3. If you haven't gone to HTTP2, then definitely go there. You're going to gain a whole bunch. Getting to HTTP3, unless you're doing like next gen things or things that are very server push oriented, or your client base is in a mobile world that's like truly mobile, and they're traveling and things like that, I'm not really overly compelled. So while I think HTTP3 is cool, that's it. It's cool. Am I going to go to it? Nah. Probably. So I don't see a reason to kind of go to it for a while.
These are the kind of things that I would just imagine HTTP4 coming along, and before anybody's even on HTTP3, or this is so much more impressive, and so you see the switch to that. Do you see that kind of thing happening here, where the incremental change between 2 and 3 doesn't seem to be that dramatic in terms of feature sets?
Well, so the question was, would we go to an HTTP4 before we get to a 3? I mean,
Before 3 is adopted, right?
yeah, the only reason I would, if the adoption rate is so abysmal, so it's because it's so complex and they come out with an HTTP4, I don't even know what that would look like, honestly. So I don't even, I would think probably what would happen is they would probably add new revisions to HTTP2 to clean up some of the multiplexing issues, that would probably be what they do. Is they probably do a combination. They would probably send the right hints back to the client, to say, hey, should you be in multiplex mode or should you be in individual connection mode? And maybe they start upping the limits that you can have like 50 connections from a single client to a server. Because honestly, oh, what were the articles? Like, this is even like, even 5 to 10 years ago, you can actually have like a single web server like have like almost 1 million connections at the same time. Now, when I say 1 million connections at the same time, it's probably more like a chat bot or something like that. But the networking stacks have become so solid and advanced that you can have so many connections at the same time, and then bandwidth is so huge that really you're probably just running into probably more memory issues. But if you have the nice I/O and you can bypass the the memory, then a single server can really push out a whole lot, either in 1.1 or in 2.
Thanks.
Yep. Yep. Yeah. I think we're out on time there. But thank you very much.